We have this bounded region. The region is bounded by these graphs, and what we want to do is take the bounded region and revolve it around the line x equal to 6 and then find the volume of the solid of revolution. So this is the graph for y equal to the square root of x. This is the line y equal to 0. This is the line x equal to 4. And this is the line x equal to 6, which is the solid of revolution. And so we want to revolve this bounded region around this line. And notice that when we revolve it, we'll get a hole in the middle. Since the axis of revolution, which is the line x equal to 6, is vertical, we'll fill the bounded region with horizontal rectangles. And then if we take each rectangle and revolve it around the axis of revolution, then we'll get a disk with the hole in the middle. And therefore we'll need to use the washer method to get the volume of the solid of revolution. And so if we take this rectangle right here, and if we revolve it around the line x equal to 6, and then we'll get a disk that looks like this. And so the disk will have a hole in the middle. And so the disk will look something like this. And since we have horizontal rectangles, we need to rewrite the equation y equal to the square root of x, so that x is a function of y. So we need to do that so that we can set up the integral in terms of y and to find the volume of the solid. And so first we need to figure out what the outer radius and the inner radius. The outer radius will run from the graph to the axis of revolution. The inner radius will go from the line x equal to 4 to the line x equal to 6. The outer radius will go from the graph x equal to y squared to the axis of revolution, which is x equal to 6. So the graph is x equal to y squared. The axis of revolution is x equal to 6. And so the radius from here to here will be 6 minus y squared. This is the vertical line x equal to 6. This graph is x equal to y squared. And therefore the radius from here to here will be 6 minus y squared. And so that's what we get for the outer radius. Now for the inner radius, which is from here to here, this is the line x equal to 6, and this is the line x equal to 4. And so the inner radius will be 6 minus 4, which is 2. And now we can set up the integral to find the volume of the solid. And for this solid of revolution, notice that y ranges from 0 to 2, because this point right here is the point 4, 2. And so y ranges from 0 to 2. And so for our integral, the limits of integration will go from 0 to 2. And again, since we have a hole in the middle, to get the volume of the solid of revolution, we'll find the volume of the entire solid and then minus the volume of the hole. And that will give us the volume of the solid that we want. The volume for the entire solid will be pi times r sub y, r of y squared dy. The volume for the hole is pi times r of y squared dy. and we can combine them like this. So this is r of y squared, the big R, minus r of y, the small r. The radius for the outer radius was 6 minus y squared. The inner radius was 2. And if we simplify this, we'll get 36 minus 12y squared plus y to the 4th. And then 2 squared is 4. 36 minus 4 is 32. Antiderivative for 32 is 32y. Antiderivative of y squared is y to the 3rd divided by 3. Antiderivative for y to the 4th is y to the 5th divided by 5. And then evaluate from 0 to 2. So we put 2 here, we'll get 64. If we put 2 here, we get 8. And then 12 times 8 divided by 3 is 32. And if we put 2 here, we get 2 to the 5th, which is 32 divided by 5. And then when we plugged in 0, we get 0, 0, and 0. And so 64 minus 32 plus 32 fifths is 192 over 5. And then times pi. So the volume of the solid of revolution is 192 over 5 times pi.